Lesson number 24, Daily Summary. In this lesson, we see how we can use part of the quadratic formula to determine the nature of the roots of a quadratic equation, and we discover a brand new set of numbers called the complex numbers. I will define nature and complex numbers in this lesson. Number one, look at graph D, whose equation is y equals x squared minus 4x plus 5. Notice that there are no x-intercepts. This parabola is entirely above the x-axis. We know we can use the quadratic formula to find x-intercepts. We saw that last class. So if we just change this y to a 0, which is exactly what we've done here, then we know solving that equation is akin to finding x-intercepts. And the quadratic formula can solve that equation for us. But we know that there are no x-intercepts. So what is going to happen when we try to use the quadratic formula to solve for x-intercepts when there aren't any? Well, let's give it a shot. So the equation is currently in our standard form, so we're ready to right away pick off the values of a, b, and c. A is 1, b is -4, c is 5. And then we'll plug into the quadratic formula. It's blank right here. Can you fill in the letters a, b, and c? Maybe pause the video here. Don't put numbers, but just put the letters a, b, and c, just as a quick pop quiz that doesn't count for anything. Come on back when you think you've got it. Okay, so hopefully we wrote that down, but it's okay if you don't have it memorized at this moment. And then, like I said before, I like to replace all of the A's, B's, and C's with empty parentheses, waiting to receive the specific numerical values of A, B, and C. And so now we'll put in the 1 and the -4 and the 5. So the first parentheses is a B, that's a -4. Next parentheses is again B, that's still -4. A is 1, C is 5, and down here A is 1. Let's do some arithmetic now. -4 is 4, plus or minus square root of -4 squared. Careful, is that positive or -16? It's positive. Minus 4 times 1 times 5, that's 20, all divided by 2. Equals 4 plus or minus the square root of -4. Well, that is problematic. All divided by 2. And I say it's problematic because we know that the square root of -4 is not a real number. And so we're stuck. So number 2, what do we do with the square root of -4? As I just said, square root of a negative number is not a real number, but can we give meaning to the square root of a negative number? Yes, mathematicians have created a number system called the complex number system, and these complex numbers allow us to work with the square root of a negative number. Complex numbers are used in many fields, such as engineering to find quantities involved in electricity, and in medicine to calculate flow of blood in the bloodstream. Before we discuss the square root of -4, let's start with the square root of -1. The question of how to define square root of -1 arose when 16th century Italian mathematicians tried to solve cubic equations, for example, x cubed minus 15x equals 4, and their efforts led to the invention of a new class of numbers beginning with this definition. We denote the positive square root of -1 with the letter I. That is, we're going to let I represent the square root of -1. It is not uncommon in math to let a letter represent a famous useful number. So for example, pi is a Greek letter, but you all know that it also represents a famous constant in mathematics. It's right around 3.14. We just call that number pi, the exact number. You might not have heard of the number e, but maybe you've heard of it. It's around 2.718, and it's another famous irrational number where, again, we use a letter to denote this specific number. So here's another instance of that. We are letting the letter I represent this specific number, the square root of -1. So how does that help us? Well, now we can find the square root of any negative number using our product rule from a few lessons back. For example, square root of -4 is the problem at hand. We changed that -4 into -1 times 4. Okay, no funny business there. And then we split that into 2 radicals. We've seen that many times now. And then the square root of -1, anytime we see the square root of -1, we are now welcome to replace that with the letter I, because the square root of -1 is called I. And so this becomes I times 2, right? The square root of 4 is just 2. And then typically if you have like a rational number and an I, you'd put the rational number first. So 2I instead of I2. But the square root of -4 is 2I. What happens if you don't have a perfect square like 4? Okay, square root of -15. became square root negative 1 times 15, split into two square roots. Again, square root of negative 1 becomes I, and so we get I square root of 15. I know that we put the I at the end here and in the beginning here, and the reason we don't put the I at the end, you could totally put square root of 15 I, but if you're just a little bit sloppy with that square root sign and you make it a little bit too long, all of a sudden the I looks like it's inside. And so to avoid that possibility, if there's still a radical floating around, we usually put the I in the front so that there's no chance of confusing it with being on the inside of that radical. How about square root of negative 12? Okay, negative 1 times 12, split. Square root of negative 1 is going to become I right there. But the 12 we can go further with. Square root of 12, that becomes square root of 4 times 3, because we're going to take advantage of the fact that 4 is a perfect square. And then we split, and then the square root of 4 comes outside as 2, and 3 has nowhere to go, so it stays inside. So we have I times 2 times the square root of 3. Typically, you'd write those factors in this order. The rational number part first, then the I, then the square root. So in general, we define the square root of negative k to be I times the square root of k. And in fact, this is okay for with me if you just use that as a shortcut. So for example, if you have the square root of negative 7, and you just say, oh, square root of a negative just becomes I times the square root of the same positive number. Okay with me if you don't go through the details that we just went through. Numbers of the form a plus bi are called complex numbers if we let b equal 0. So that's the I part disappearing. So a plus nothing is just a, and you get all the real numbers. A is allowed to take any real number value. So that means that the real numbers are automatically complex numbers. All of the real numbers are inside of this larger set of complex numbers, but then the complex numbers includes many numbers that are not real numbers. So let's finish solving the quadratic equation we started with. We left off right here. And now we're going to split this into two fractions. That's old for us, right? 4 over 2 plus minus root negative 4 over 2. That's here. 4 over 2 becomes just plain 2. Negative on the inside becomes I on the outside, and then the negative 4 becomes positive 4 at that moment. Square root of 4, that's easy. That's plain old 2 with no radical anymore. And then the 2's can cancel, and we just have an I left over from the second fraction. So 2 plus or minus I. Those are the answers to this quadratic equation. It is not a surprise that we didn't see X-intercepts, because you're not going to see 2 plus I when you graph anything, because the graphing that we do is all in the real numbers. And so any imaginary number that pops out here is not going to appear as an X-intercept. Is there a way to figure out how many solutions or what kinds of solutions a quadratic equation has without going through the entire quadratic formula calculation? Below each graph, you'll see the nature of the solutions of each quadratic equation, which is just describing the X-intercepts. The solutions of the quadratic equation correspond to X-intercepts. Recall that a rational number can be written as a ratio of two integers, for example, 1/2, but numbers with radicals in them, like square root of 10, are irrational. Obviously, something like square root of 9 is rational because there isn't really a radical there. So square root of any number that isn't a perfect square, any positive number, not a perfect square, those are irrational. Okay, let's take a look at this graph. I've got X-intercepts here and here. There are 2 of them, and they appear to be rational numbers, -6 and 1. Very nice numbers. 2 rational solutions is what we call the nature of the solutions there. On this top right graph, it looks like there's exactly 1 X-intercept. Looks like it's right around X equals 2. So in this case, there's not 2 solutions, there's just 1, and it is again rational. 2 is a rational number. There's no radical inside of there. Okay, this one, there are 2 X-intercepts, so there's the 2 part. But we saw, like, I think it was last class, like -3.449, and then it went on. It actually went on forever, and 1.449. And it went on forever. And those were 2 irrational numbers. They still had square roots left in them after we did the quadratic formula calculation. So 2 irrational solutions there. And then finally, the one we just did, this one has no X-intercepts, right? The graph never touches the X-axis. But if you actually do the equation solving, which we did with that square root of -4 on the last page, you do get 2 solutions. We got 2 plus or minus I. That is 2 plus I and also 2 minus I. So there are 2 solutions. They have i's in them, and that means we're going to call them imaginary solutions. Okay, number 8 has a definition. So the nature, I said I would define it. Nature just means how many solutions and what kinds of numbers are they? Are they rational, are they irrational, or are they imaginary? How many and what kind? Okay, for the quadratic equation, we're defining this thing called the discriminant. It is b squared minus 4ac. Where have we seen that expression before? Well, that is exactly the thing inside of the square root in the quadratic formula, right? Negative b plus or minus square root of b squared minus 4ac. So the discriminant is just the fancy word for the name of the thing inside the radical in the quadratic formula. Calculate the discriminant for the 4 equations below, then fill in the last column by copying the information below each of the graphs A, B, C, and D. Okay, first one. 0 equals x squared plus 5x minus 6. So the discriminant is b squared minus 4ac. So b squared minus 4ac. So in this case, the b is the number touching x, positive 5. A is the number touching x squared, positive 1. C is the number not touching any x, that's negative 6. And now we're just doing the arithmetic here. So that's 25. 4 times 1 times 6 is 24. And I see 2 negatives, or a minus sign and a negative, and that becomes a plus. 49 is the discriminant. Okay, let's try these other ones. We'll do them quicker. The next one, b squared, negative 4 squared minus 4 times 1 times positive 4. 16 minus 16 is 0. That's the discriminant for that quadratic. Next one, 2 squared minus 4 times 1 times negative 5, which is 4, and then 2 minuses make a plus, and that's 20. So 24 is the discriminant here. And then the last one, negative 4 squared minus 4 times 1 times 5. 16 minus 20, negative 4. Okay, and then we're just copying the graphs up above, the information written right below each graph. So the top left graph said 2 rational solutions. The top right graph, you can see it on your page, but not on my smartboard right now, said 1 rational solution. So I'm just copying the nature for each graph. The bottom left one said 2 irrational solutions. And then the bottom right graph said 2 imaginary solutions. And it turns out we can get those answers, that right-hand column, we can get them just by looking at these numbers, the 49, the 0, the 24, and the negative 4. We can figure out how many solutions each equation has and what kind of numbers they're going to be, rational, irrational, or imaginary. In fact, like I said, you could see it on your page, the information up above, but I can't see it here on the smartboard, and I'm not looking at a piece of paper right now. I just used a simple formula that I'm going to share with you to get these answers just off the top of my head here on the right-hand column. So let's think about the quadratic formula, full-fledged quadratic formula. So again, it's x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now, in the first row, the discriminant was 49. And where will that 49 end up in this quadratic formula? Well, it's the thing under the square root. It's the entire thing under the square root, so it goes there. And the square root of 49 happens to be a very nice number, it's 7. And so when I do this quadratic formula calculation, the square root completely disappears, and I just get, nice integer number on top and another integer number on the bottom, and the whole thing, therefore, is rational. And so I know for sure that the kinds of solutions I'll get will be rational. And how many will I get? Well, I'm going to get 2. One for the plus square root of 49 and one for the minus square root of 49. And so 49 gives me 2 rational solutions. Same thing would have been true if it were the, instead of 49 down here, if we had like 16, because the square root of 16 is a nice integer number. So really, any perfect square you give me, for the discriminant, and the conclusion is always the same, 2 rational solutions. Okay, so what if we move on to the next row? So instead of 49 for the discriminant, we have 0 for the discriminant. So we're putting that as the entire thing under the radical. So how much is the square root of 0? Well, it's just plain 0. So again, the radical completely vanishes in this particular case. Square root of 0 is just 0, and so we get negative b, whatever that is, plus or minus 0 divided by 2a without a radical. Okay, so then for sure that's going to be a nice rational number because the square root disappeared. We just get integer over integer. So I agree with this rational here, but how many solutions are there? Why aren't there two? There's a plus and there's a minus. But if you add 0 to the negative b, or if you subtract 0 from the negative b, you're still going to get negative b. It's exactly the same solution twice. So the plus or minus only in this special case of 0 actually condenses to a single solution instead of having the two separate solutions. So anytime you have the number 0 as your discriminant, the conclusion is always the same, rational all day, every day, but only one, only for the case where the discriminant is 0. Okay, let's take a look at the next discriminant. It's 24. I'll put that right there. Now it happens I can simplify the square root of 24. You write it as the product of 4 and 6. Don't even need to get into that detail for this one. The fact is the square root of 24 is an irrational number. If you imagine writing it as a decimal, it will go on forever, never repeating. And so I don't care what the b and the a are sitting in the rest of that quadratic formula, but this thing with the square root of 24 in it is going to give me an irrational number. And how many irrational numbers will it give me? Well, it's going to give me two, one for the plus square root of 24 and one for the minus square root of 24. So our conclusion here is two irrational solutions. And so that is the case for any number like 24 that is not a perfect square. You give me any positive number inside of that radical that's not a perfect square, I'm going to get two answers, one plus, one minus, and they're both going to be irrational because that square root is still going to be in the expression at the end of the day. Okay, and then finally the last one is the square root of -4. This is the bottom row now. So if you put a -4 in there, well, that is a negative number, and we know that the square root of a negative number is imaginary. And so it doesn't matter that 4 is a perfect square. It could have been -5 under there. The fact that it is a negative number is the end of the ball game. You give me a negative value for the discriminant, and I know that they're going to be imaginary solutions. So that was this answer here. Negative discriminant, right away, it's going to be imaginary. And how many solutions will we have? Well, there's a plus square root of -4, and there's a minus square root of -4. So again, we get two solutions, one for the plus, one for the minus. And that's true for any negative discriminant. And so I'll just point out that really the nature of the solutions is 2 all the time, except in this one special case where the discriminant is 0, because adding 0 and subtracting 0 is the only time where the number doesn't change. Everything else is 2, and then based on what kind of number you have, perfect square, 0, not perfect square, or negative, your conclusions are either rational, irrational, or imaginary. So this is summarized all on the next page. If the discriminant is 0, one rational solution. If the discriminant is negative, two imaginary solutions. If the discriminant is positive, we actually have to ask ourselves a follow-up question. Then we need to know whether the discriminant is a perfect square or is not a perfect square. If it is a perfect square, then that square root disappears and you get rational solutions. How many? 2, always 2. If the discriminant is not a perfect square, well, you still get two solutions, but in this case, the square root will still be in the final answer, and you will get two irrational solutions. So as you're working on this activity, I want you to treat the discriminant as being a shortcut, like a special case that, that gives you information without doing the full-fledged quadratic formula. So I'm just going to do the discriminant part of number 1 here. So the discriminant, again, b squared minus 4ac. So 5 squared minus 4 times 2 times -2. 25 minus makes plus. 4 times 2 is 16. 41 altogether. So what is the nature of the solutions? Well, 41 is positive and not a perfect square. Therefore, looking at the work up above, two irrational solutions. That is the nature. If you were to solve the full-fledged equation right up here, you expect two irrational solutions. And then the next thing says actually calculate the solution. So I'm going to show you, I'll just get this one started here. Remember the quadratic formula, negative b plus or minus square root b squared minus 4ac, all divided by 2a. Okay, so negative b, that is -5 plus or minus. Okay, now we have already done b squared minus 4ac, and I don't want you to do it again. I want you to just plop the 41 in there. No need to recalculate b squared minus 4ac. Done. And then it gets divided by 2a. 2 times 2 is 4. So there you go. Those are the two solutions, -5 plus or minus square root of 41 divided by 4. And so it's not that the discriminant is giving you more work to do. It's just sort of pulling apart some of the work you have to do anyway if you're using the full-fledged quadratic formula.